So before we talk too much about the rate law, let's take a quick recap of what we know so far, because it's going to play into this a fair bit. Number one, we know that reactions happen at a measurable rate. We know how we can measure it. We know what we are actually measuring. We can measure either the products or the reactants, depending on what's a little bit easier to use, and we can manipulate the rate. We can change the rate. We can change the conditions like concentration, temperature, presence of a catalyst, things like that. Okay, so how does all that play into the rate law? Well, first of all, let's talk about what the rate law is. It is the relationship between the concentrations of reactants and other stuff and how fast the reaction is going to go. So we'll set a bunch of conditions. So you'll see in questions it'll says at this temperature, blah, 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 blah. Where we never actually use the temperature, it's just that we know that if we change the temperature, the number would be different. And if there's a catalyst, we would have to say that in the thing as well. Or there would be a way we would know it's a catalyst. And I say it like that because one of the first questions you're going to get is to identify which one is a catalyst. And yeah, you'll know. Okay, one of the things about the rate law, and this is one of the initial things that's difficult, but you'll get past it, is that it cannot be determined by looking at a reaction, because the reaction equation is really just a summary of all the stuff that goes in and all the stuff that comes out. We can't look at that and know exactly how the molecules go about it, how the bonds break, how the bonds form. So we have to do this experimentally, or we at least have to have experimental data to work with. Okay? So that's going to be kind of key as well. All right, so what does it look like? Well, for a reaction, and I'm just going to use this generic one where I've got the reactants, I've got products, I've got balancing numbers. The rate is going to be some K value, that's a constant, I'll come back to that in a second, times the concentration of one reactant raised to an exponent times the concentration of the other reactant raised to a different exponent. And if there's more reactants, then yeah, there's going to be more of those things with raised to an exponent. K is the rate law constant. Now you'll notice the rate law only has concentration terms. So K would take care of the other things that will change a reaction. Hey, did you change the temperature? Is there a catalyst that was there before and isn't there now, or the other way around? The exponents, they are not, as I said, they are not balancing numbers. It might turn out once in a while that you got a balancing number of 2 and an exponent of 2, and that's an interesting coincidence, but it's nothing more than that. It's definitely not a pattern. When you are working with a rate law, you're going to first have to determine the exponents from experimental data. You're then going to calculate K, and then you're going to determine the units of that value of K. And I'm going to put it to you this way. Coming up with the value of K is just straight button pushing on a calculator. It's not that impressive. Coming up with the units of K, now that takes some thinking, so that's where all the effort should be. Paying attention to the units. Don't just, units, schmunits, and then skip it. That's where I'm looking for, do you know what you're doing? Okay, we're going to start with some math before we get into the weird stuff. So if you had a simple expression like this, where I've got some number raised to an exponent and it's giving me another number, because again, we're going to have numbers raised to some exponents. If I had this one, 1 raised to the exponent of 0, well, I get back a 1, because anything raised to the exponent of 0 is a 1. So if I turned around and I did not know the exponent, and I knew my number was 2 raised to some exponent, and that gave me a 1, the exponent is 0. If I had 2 raised to some exponent of 1, or raised to the exponent of 1, I'll give you a second to punch that in. No, I won't. It gives me a 2. 2 to the exponent of 1 is 2. Okay, well, what if I did not know the exponent, but I knew that I had a 3 raised to some exponent, and that gave me back a 3? Obviously, the exponent is a 1. How about this one? If I have 2 raised to some exponent, and that gives me 8. Now, that probably took you a little bit longer, but you still probably came up with 2 to the exponent 3 gives me 8. If you said 4, you're thinking multiplying, not exponents. Okay. Let's look at this reaction. Now, I don't care what the products are, products on that side. I don't care what the products are because the products aren't important. The rate law is all about the reactants. I don't really care about those balancing numbers, but I brought them along just for the fun of it. Okay, I'm going to talk about bromate and bisulfite so that I'm not running around saying Br3 to exponent minus 1. It's just too much. Bromate, bisulfite. I'm going to have a table of experimental data where I'm taking the reaction, I run it the first time as a baseline, and then I change the concentration of something. Now you'll notice, and we'll break this down in a second, but if I'm only going to change the concentration of one thing at a time so that I can monitor what's happening with it. Now these numbers look a little bit intimidating at first because they're decimals, and that sometimes gets people weirded out, but we're going to just walk it through, and you'll notice that I'm going from, in the bromate column, from 0.02 to 0.04. So I've raised it by a factor of 2. I've doubled it. Okay, and the same kind of thing happens around. All right, break it down a little bit more. If I compare reaction number 1 with trial number 2, let's call it trial 1 with trial 2. Well, what I have is there's change in the concentration of bromate, and that's it. So any change in the rate is only caused by the bromate. So all I have to worry about is what's going on with bromate, and then I can get the exponent for bromate. If I look at 1 and 3, then the only concentration that's changing is the bisulfite, so any change in the rate is caused by the bisulfite. If I were to look at 2 and 3, then both things are changing. One is going down, one is going up, the rate's doing its own thing. That wouldn't be impossible, but don't do that. Okay? Work with things where only one thing changes. It will not always be 1 and 2, 1 and 3. It might be 1 and 2, 2 and 3. It might be 1 and 2, 2 and 3, 1 and 4. It can be any combination, but look for things where only one thing is changing. At least only one concentration is changing. Obviously, the rate in most cases is going to change. Okay. If 2 things are changing, then the rate becomes a bigger job to work with. So avoid it if you can. Okay, let's go back and take a look at trial 1 and 2. The change in bromate is a double, multiplying that by 2. Bisulfite rather, no change, so let's ignore it. The rate change, if I look at the new rate divided by the old rate, it gives me a factor of 4. So I've got some number, 2, raised to an exponent, and it gives me 4. Well, the exponent on 2 that gives me 4 is going to be also a 2. So 2 to the exponent 2 gives me 4. The number I'm looking for is that exponent. I need that exponent 2. So now my rate law starts to build where I've got the bromate, BrO3 with exponent, that's not the exponent, the charge of -1, that has an exponent of 2. Okay. Now I'm going to look at trial 1 and 3 because there's no change in the bromate. And there was a change in the bisulfite. It was also multiplied by 2. By the way, it doesn't have to be multiplied by 2. It could go up by some other number. I need to know what it's going up by. It's not always just a magical 2. The change in rate there is new rate divided by old rate, and that came up to 2. So when I double the bisulfite, I also double the rate. So now what I'm doing is I'm looking for the exponent on 2, that's the doubling of the concentration, that will give me a doubling of the rate, also a 2. Well, 2 to the exponent 1 gives me 2. So now my rate law is built a little bit further in that the bisulfite has an exponent of 1. Okay? If that doesn't make sense, go back and look at the math again. What did I change my concentration by? That's my big number, 2. And then what exponent do I need on that to give me what the rate changed by? Okay, it's really that x to the exponent m equals y business. Rate law constant. Okay, you're going to pick a trial. You're going to substitute known values for that you have, put them in, you're going to solve for k, and then you're going to solve for the units of k. We're not going to get all the way through that because we want to talk about that in a little bit, and it would just make this a whole lot longer. I pretty much always use trial number 1. It's usually the simplest, but it could be any one of those trials. It's all the same reaction. It's following the same rate law. But for me, I'm going to use my rate law as I've got it. I'm going to substitute the values in that I know. So for that trial 1, that was the rate. Those were the concentrations. Those were the exponents that I figured out. Then I'm going to do the math. Now, if you're not super familiar with scientific notation, you should probably get super familiar with scientific notation during this section. Okay. Solve for k, I get 166.7. What about the units? Well, The units are going to come a little bit later, but we are going to, well, if you think back to your exponent laws where you're doing x's and y's, that's going to come into play here because I've got units to exponents as well. And as I said before, the units are the part that shows me that you know what's going on more than anything else. Okay, so like I said, we'll talk about the units when we get to class. The units were, well, I'm just going to leave that hanging there. Okay, so what have we accomplished today? Well, we know what the rate law definition is. We know what it means. By the way, what happens if I change the catalyst? Well, that's going to be factored in with K. What if I have to change the temperature? Factored in with K. So are we going to have to work with that? Not really, no. So for us, rate law is going to come down to, in almost every case, concentrations and a big table of data. Anyway, we'll talk to you another time.